всего сейчас разговоры идут про эту вашу реактивщину. Но эта тема все равно остается непонятной хотя бы потому, что зачастую излагается разработчиками со свойственными им, ну, нам, образом мышления и особенностями. Иногда для объяснения таких сложных идей нужен взгляд кого-то принципиально иного по майндсету, например, биолога. Но не случайного, а такого, кто реально бы шарил в теме. Я бы, честно говоря, сам не поверил в то, что такие люди есть, если бы сегодня на Snow One у нас не был доклад как раз от такого человека. Грейс Jansen, Developer Advocate в IBM и восходящая звезда западных конференций по Java, да и не только. Она уже сейчас известна многочисленными гайдами и туториалами по самым разным темам вокруг разработки ПО. А недавно она стала и соавтором книги по реактивным системам. Именно о них она и собирается рассказать здесь у нас на Snow One. Однако в силу некоторых проблем, свойственных нам всем со здоровьем, она сделает это заочно. Мы покажем предзапись ее доклада, сделанную специально для Snow One. А возникшие у вас вопросы отправим ей позже для ответа в комфортное время. Так что все равно задавайте вопросы, обсуждайте доклад, а мы постараемся донести до нее атмосферу конференции, только сделав это чуть позже и не расплескав ничего по пути. Итак, устраивайтесь поудобнее, подлейте напитка и приготовьтесь. Я приглашаю вас в путешествие по реактивному миру вместе с Грейс Jansen.
Hi, and thanks for having me. It's great to join you all at Snow One, and thank you for joining my session, Reacting to an Event-Driven World. My name is Grace Jansen, and I'm a developer advocate at IBM based in the UK, and I primarily focus most of my time on sort of Java, the JVM ecosystem, and specifically sort of reactive technologies and deploying these sort of Java cloud-native applications into cloud environments. So first off, let's get some coffee, because every conference talk needs a coffee demo application. So we've got here a Barista example, so a coffee demo example, and you can find this actually, it's been created by our cousins over at Red Hat, and you can find it in open source GitHub. There's a link at the bottom of the slide for that. So in this example, we have coffee lovers coming in and making a HTTP request for a coffee to the coffee shop, and that coffee shop then passes that HTTP request for a coffee onto the barista. Now, the issue with this is that because of the nature, so the blocking nature of HTTP requests, is that in this scenario, the coffee lovers would have to wait at the till at the coffee shop for the barista to finish each of their coffees. They're not able to go and sit down and relax and wait until their coffee order is complete because they're blocked by the fact that they have to wait for the barista to bring their coffee order back before they can go and sit down and before the next person can order. So in this scenario, many people would just jump to the answer of, oh, we'll just put in event-driven architecture. So we've got here sort of a basic diagram of what event-driven architecture is really about. Essentially, it's a really popular architectural approach that puts events at the heart of our systems. So it's all about having records of sort of state changes within our application and creating events for them and creating a log of some kind that sequences the creation of these events in this sort of log. You can see all this messaging backbone we've got in the center of our diagram here. You can publish events, you can also consume events, and you can do both depending on what your microservices need to do. So let's take a look at what happens when we introduce this into our Barista example. Well, in this case, we have our coffee lovers still creating their coffee order requests using HTTP to our coffee shop, but now when the coffee shop receives those requests, it puts those requests on an event backbone utilizing this event-driven architecture, so it creates an event for them. Then the barista is able to consume those events, so read the coffee orders off the event backbone, and it can then make them, and then once it's created them, it can update a board which tells the coffee lovers when their coffee order is complete and they can come and collect it. So it means that our coffee lovers now aren't stuck waiting at the till for each of their coffee orders to be served before the next person can be served and before they can sit down. Now, once they've created that coffee order, they can go and sit down, chat about Java with their friends, as we all love to do, and they can essentially just periodically check the board to see when their coffee order is done, and then they can go and collect their coffee order. So it means it's a lot more asynchronous and not more sort of non-blocking, so that's a great sort of step forward. A great way of achieving this event-driven backbone and event-driven architecture is by utilising a popular tool called Apache Kafka. So for those who haven't heard of it before, this is an open source distributed streaming platform, which enables you to sort of keep stream history. It has sort of immutable data. It makes data really highly available and very, very scalable. So once we've introduced this event-driven backbone into our application, what does this mean? Well, it sort of leads to the question of, okay, now that we've introduced it, is our coffee shop now non-blocking and highly responsive as we all want our applications to be, and as, users nowadays expect our applications to be all the time? And this translates as, is your microservice system non-blocking and highly responsive? And people often jump to the conclusion of, well, yes, I'm using Kafka, it must be. That's not the complete answer. Although Kafka is a really good tool, as I said, it's not enough just to put in a tool as sort of that one layer of your application, that one data level, and expect it to be reactive and responsive and resilient all the way through your application from end to end. So the short answer is we cannot just use Kafka to create a reactive application. We need to think about the entire application we've designed and developed, and also how we can enable things like the configuration within Kafka to be more reactive and responsive and resilient. We can't just shove it in and expect it to work straight out the box either. So this is where Reactive Systems comes in. Reactive Systems is about creating really reactive and responsive systems from end to end. And it's based on something called the Reactive Manifesto. So this was created back in the original was in 2013, the second version 2014, and it's basically outlining the key behaviors and characteristics we want to be seeing from really reactive applications. So the underlying behavior that we need in these applications is having this message-driven form of asynchronous communication within our application. It's all about decoupling the components within our application by having this asynchronous communication. Interestingly, it actually used to be event-driven at the bottom of this sort of manifesto in the original 1.0, but in 2.0, the Reactive Manifesto 2.0, they switched to message-driven, and there's a whole blog post on why they did that. So if you're interested, you can go and check it out. But let's take a look at what the difference is between them and whether this affects whether Kafka can be used for it. So we've got a definition here of messages and a definition for events. So for messages, we've got essentially it's an item of data sent to a specific location, whereas an event is a signal that's essentially just emitted by a component upon reaching a given state. But interestingly enough, you can actually have a message that can contain an encoded event in its payload. So you can kind of have this weird mesh of both. But when it comes to Kafka, it really doesn't matter which you use. If you look at the Apache Kafka website, it actually never mentions events or messages. In fact, it mentions records. It references this term called records. So really, Kafka has deliberately moved away from the word events and instead uses records now so that it can be used for both message-driven and event-driven applications. So actually, Kafka can be an excellent tool to use for creating this message-driven asynchronous backbone of communication within our application that we need for reactive systems. But as we said, it's not the end. It's not the end solution for reactive. There are 3 other characteristics we need to be thinking about. So let's take a look at why they matter by taking a look at potential problems we could sort of come into with our Barista example. So with our Barista example, we only had 3 coffee lovers in it. But actually, there are more than 3 coffee lovers in the world, so let's see what happens when we increase the load on the system by increasing the number of coffee lovers making coffee orders. So the more coffee lovers, the more coffee orders, and this means that our system's under greater load here. Now, although our coffee lovers aren't blocked because they can go and sit down, chat about Java, whilst their coffee orders put on the event backbone, we do have a form of blockage and a form of potential contention within our application. Because although we've got this fantastic sort of buffer in the event backbone, we only have one Barista microservice here who's able to take those requests, process them, and provide the coffee they need. So in this case, we have this potential point of contention that's slowing down our system and stopping us from being really responsive and reactive. And this is where the behavior or characteristic of elasticity comes into play. Elasticity is all about being able to scale up and scale back down again depending on the load to our system. So scaling up so that we can provide a system that's really responsive and is able to deal with increase in load, but also scaling back down again so we're as cost effective as possible. So in this scenario, using the elastic behavior, we would then be able to scale up the number of baristas as that load increases so that they could better respond to the increased number of coffee orders, so we're still providing that very fast service and that responsive service that our users expect. Another issue we could come across is, okay, in this example, we've added an additional component to our application. So this component here is the coffee serving table. And in this example, the barista, in order to serve up the coffee, has to place it on the coffee serving table for the coffee lovers to come and collect. This is essentially a representation of, say, an external service, like a database, for example, or even perhaps a sort of microservice that's a downstream microservice that perhaps has to do some additional processing on that request. Or it could be an external service or an external application. So in this case, what happens if, for example, our coffee lovers are being a little bit lazy, they're not coming up to collect their coffee orders from the coffee serving table, so now the table's full and our barista's juggling coffee because they can't put it down on the table. Well, in this case, this is essentially representing that third-party component or that downstream component going down, becoming unavailable or potentially getting stuck in some kind of process. And that means that our barista is now stuck and can't continue processing those coffee orders. So at this point, we've potentially got a failure on our hands. Our app might become unresponsive. Our coffee lovers aren't able to get their coffee. We're not being reactive and responsive. So this is where resiliency is really important. Building in resiliency into our application to gracefully handle those potential failures, regardless of sort of how catastrophic they might or could be. It's about building in this resiliency. So in the case of the barista example, what we could do is integrate something like back pressure here, so we could have some feedback from the downstream components to the upstream components to rate limit the requests coming in, or we could introduce a circuit breaker so that this particular barista microservice is given a chance to recover, or the downstream component a chance to recover, and we could send those requests to an alternative barista and serving table. So in this case, we'd be able to gracefully handle this potential failure point and not end up with an unresponsive application. And this all leads to the last characteristic or behavior in the manifesto, and that's responsiveness. So being reactive is all about being able to respond to event changes and state changes within our application so that we can really provide this reactive experience for our end users. So these behaviors are really important to enable within our applications to make sure that they're really responsive to the event-driven world that we now live in. But how do we actually go about building these reactive systems? Everything I've talked about so far has been fairly high level based on generic behaviors. Well, we've got a basic application here just to demo the various different levels we need to be considering when it comes to creating an end-to-end reactive application. Kafka is a fantastic tool, like we mentioned, for that data layer and enabling that decoupling of components by providing this asynchronous messaging backbone. But we also need to think about our application itself. So, for example, one layer we need to think about is how do the various components of our application communicate together? So, in this example, how does Microservice 2 communicate with Microservice 3, for example? And this is where reactive architecture patterns can come in really handy. There are many, many different types of reactive architecture design patterns that you could utilize. We've just picked out 4 of the common ones that we've come across. So they include things like CQRS, which stands for Command Query Responsibility Segregation. So that's all about really separating out the read and the write APIs to enable high availability of that information and the data within your application. We've got circuit breakers, which I mentioned could have been a potential solution for our barista example. Now, circuit breaking is really similar to sort of the electrical engineering version of it in software. So in circuit breaking in software, an upstream component recognizes that a downstream component is perhaps under load, stuck in a process, or perhaps has failed and gone down. And it can temporarily put a stop on requests going to that microservice and instead reroute them to replica microservices. And then it gives that downstream component a chance to recover, get better, get through whatever process they might be stuck on. And then once they're back to being healthy again, that upstream component can reinstantiate that request route down to that microservice. Then we've got Sagas. So Saga is essentially a mechanism that takes traditional transactions that we might have maybe done in a more monolithic architecture and do it in a more distributed manner. So we create this sort of multiple microtransactions that have this fallback behavior to account for things going wrong partway through. And then we've also got back pressure. Back pressure, as I mentioned, is a feedback mechanism from a downstream component to an upstream component, which helps to rate limit. So it means that if you've got a downstream component that's under load, it can rate limit the requests coming to it from the upstream component, meaning that it doesn't go into failure, and it can recover and stay healthy, and it doesn't become a point of contention or failure within our application. So these are design patterns you can implement as sort of the scaled out view of your application, so between microservices. But we also need to think about how we make our individual, so the logic within our individual microservices, again, reactive and responsive and asynchronous. And to do this, we can enable something called reactive programming. So reactive programming is all about introducing this asynchronous style of programming into our application logic. So it's a paradigm where the logic is driven forward in our microservices via the availability of new information instead of by a thread of execution. And it's that asynchronicity that's really important in reactive. So we can implement this via several different patterns. So as many of you are probably aware, being Java programmers, there is this concept of futures which you can utilize. So futures are a promise to hold the result of some operation until that operation completes. So again, all about that asynchronicity. We can also enable reactive programming libraries. Now these libraries are essentially designed to enable you to compose asynchronous and event-based programs. And they include examples like RxJava and Small I Mutiny. And actually many of these reactive programming libraries are utilized in the reactive frameworks and toolkits that we'll be looking at later on in this presentation. And we'll be utilizing the RxJava programming library in the interactive lab I'm going to demo at the end of this presentation. There's also reactive stream specification. This is a community-driven specification that was designed to act as a standard for handling asynchronous data streams in a non-blocking manner while providing that all-important back pressure to stream publishers. And again, this reactive stream specification is also utilized by many of the reactive frameworks and toolkits, and we also utilize it in the lab we'll be using at the end of this session. So we've looked at sort of how we can introduce reactive behaviors within our microservices, how we can enable reactive behavior between the components of our microservices and at the data layer using Kafka. But how do we make sure that we're really utilizing Kafka as best we can to be as reactive as we can in our reactive systems? So we talked about the fact that it's really great for this message-driven sort of asynchronous data layer, but what about introducing the behaviors of elasticity and resiliency and responsiveness? So we're going to take a look at these in more detail. So how do we enable our Kafka to be resilient and our application to be resilient when communicating with Kafka? So Kafka is very different from sort of more traditional message queuing systems in that it actually provides stream history. So in traditional messaging systems, where a consumer reads a record reads a record, that would normally be removed. But in Kafka, that record is not removed from the topic. So both the original consumer and any other consumers can reconsume that record at a later time. So this is really important because this stream history is useful if our consumer goes down, for example, and needs to recover from a failure. So it allows applications to essentially reread those records and get back to the state that they were in, which means that it's really resilient. So we have this inbuilt resiliency just from the way that Kafka is designed, which is fantastic because we've got this immutable data and this stream history. Kafka also enables resiliency in the way that it works in terms of its brokers. So it has this inbuilt resiliency in here as well. So when you start up a Kafka cluster, it consists of a set of brokers. A cluster has a minimum of 3 brokers, which we'll see why later. And within these brokers, they're broken down into topics, and this is where we store our records. So a topic is essentially a logical grouping of a similar kind of message or record, and it's completely up to you how you define which messages or records will go into which topics. So you might have a topic, in our example, in the Barista example, we might have a topic for coffee orders, and we might have a topic for updating user information. Within your topic, you'll have one or more partitions, and these partitions are split or distributed across the different Kafka brokers. So taking a look at the brokers themselves, we have this concept of leaders and followers in Kafka. So for each topic, one of the brokers is elected as the leader, and the other brokers are then followers. So essentially, our application connects with the leader, and then replication works by the followers repeatedly fetching messages from the leader, and this is all done automatically by Kafka. So essentially we get one connection with the leader to our application, and then that information is replicated across the followers, all automated by Kafka. But what happens if, for example, our leader goes down? So that means that our application can no longer talk to Kafka. But actually, what's fantastic about Kafka is it has something called leader elections. So in these leader elections, what happens is the followers essentially automatically decide one of them is going to be the new leader, and then our application will automatically transfer to communicate with that new broker, that new leader. And then the follower will still be fetching from that new leader to replicate the data. And that means it gives broker 1 enough time to come back online so that it becomes a follower again, and we don't ever lose that connection to Kafka, regardless of whether a broker goes down or not, which is really resilient behavior, which is fantastic. And it also means that we're never losing data. Because we've got those 3 replicas, and this is where that replica of 3 is important here, we never lose the data, because even though that leader went offline, we've already replicated it into the followers. And even though say that leader went offline, we've still got 1 leader and 1 follower. So even if the second leader went down, we'd still have a follower left. So it really enables resiliency within our application, resiliency of keeping that data. We're not losing anything, and we're able to immediately reconnect to a new leader, so our application doesn't lose connection with Kafka itself. So Kafka is amazing at having this inbuilt resiliency within it. But what about our connection to Kafka from our producers and our consumers within our application themselves? So when it comes to creating really resilient producers, there's 2 things we really need to be aware of. We need to be thinking about our delivery guarantees and our configuration. So when it comes to wanting to create reactive applications, we can't do fire and forget because we want resiliency. Because essentially if we did fire and forget and the leader broker went down, you'd lose your messages. So we need to be thinking about our delivery guarantees to make sure that Kafka is receiving the records that we send to it. And there's 2 different delivery guarantees. There's at most once and at least once. So at most once, you might lose some of the messages. It's not completely resilient, but if you don't mind some of the messages going down, it is slightly quicker. But then you've also got at least once, which means that you get guaranteed delivery, but you do have to be aware that you might get duplicates. So it's important to consider, do you want at most once or at least once? You'll get different resiliency levels for each, but if you do go for at least once, you do have to be aware of things like replicas that you might get or duplicates. Then there's configuration. So there's 2 configuration values we need to be aware of. There's ACKs and retries. So ACKs essentially is short for acknowledgement, and that's about whether the records or messages have been acknowledged or received by Kafka. So you can either set ACKs to 0. 0 is for when you really don't care about getting the messages acknowledged. It's really good for fast throughput, but really not good for resiliency. So if you're looking to create a really resilient producer, I wouldn't go with 0. You could set it to 1. 1 is essentially make sure that the leader broker has successfully received the message, but it doesn't really care about the followers receiving it. It acknowledges only after the leader. So again, not wholly resilient, but a lot more resilient than 0. Or you could set it to all. So all is essentially, it waits for every replica to confirm they successfully received the message before it acknowledges that to the producer. So that's the most resilient configuration we could get for that. Then there's retries. So retries are important if the acknowledgement times out or fails. So this is an important question to consider in terms of how often do you want to retry, how many times do you retry producing the event, and how will the retry affect ordering? So that's something to bear in mind when it comes to ensuring that your record has been received by Kafka for your producers. For consumers, when we're creating resilient consumers, the configuration we need to be aware of is this offset value, so committing the offsets. So when we're consuming from Kafka, we want to make sure that all the records are read. And because of this stream history, we need to make keep track of sort of where we've read up to. And we do that by utilizing offsets. So offsets are essentially a number associated with a particular record on a particular topic. So essentially, as a new event is appended to the end of that topic, it receives the next number up. So you can see here we go 0, 1, 2, 3, 4, 5. So we need to, every time our consumers consume one of those records, they need to be committing that offset, which means that they're essentially saying, yes, I've read that message. So if I was to go down again, I wouldn't have to come back up and reread that message. I could just start at where I left off. But this does mean that you need to be aware of how you're committing that offset. And this is where you can either do auto commit or manual commit. So let's take a look at our Barista example to see sort of how it differs in terms of resiliency between these 2 ways of committing offsets in consumers. So here on the left-hand side, we've got the Barista with auto commit. So we've got a topic and we've got 3 records. We've got 3 coffee orders essentially, 1 for a coffee, 1 for a cappuccino, and 1 for a latte. With auto commit, essentially it's done, it's relying on default settings in an underlying client because there's no code in the application that specifies when it should be committed. So it's usually done on sort of a timer basis where they'll automatically commit the offset for the message that they've read from Kafka after a certain period of time. So in this case, our barista starts with the coffee order. So because we're on auto commit, after a certain period of time, this offset is going to be committed. So we've committed that offset. Unfortunately, the barista is still making the coffee, and whilst processing this record, he drops the coffee, which means this is essentially representing that barista microservice may be going down partway through processing this record. So now when the barista comes back up, it reads where it set it offset, it committed its offset, so it's already done the first one, so it'll start at cappuccino and then go on to latte, which means at the end of it all, we've only got 2 coffees when we should have 3. So you can see here how using auto commit means that your resiliency isn't quite what we need it to be because you've lost a record on the way. You can improve your resiliency by implementing a manual commit for your consumers. So manual commit is when you add the code into your application logic that determines when that offset is going to be committed. So in this case, we're not going to commit the offset until we've processed and served up the coffee orders. So until we've finished that processing of that record. So in this case, even if the barista was to drop the coffee partway through, we haven't committed the offset, so we'd know to start back at coffee when we restart that microservice. So now when we create coffee, we don't commit that offset until we serve, as you can see here. So now we're able to create all 3 coffees without any problems, and it's a much more resilient form of consumer. So you can see here how Kafka has built-in resiliency, which is fantastic, through things like its brokers, its partitions, things like its retention of the events, its stream history, and we're able to add extra resiliency into the consumers and the producers by really considering carefully the configuration that we're utilizing. By utilizing things like schemas and schema registries, we can also introduce greater resiliency because we're now able to sort of externalize the structure of the data we're sending in and we're consuming when we're utilizing our application. So schemas and schema registries can be really useful for storing these data structures and for adding in that greater resiliency. What about scalability? So elasticity and scalability. So Kafka does have sort of elasticity built in. So if we take a look at that cluster again, those different brokers and partitions, as I said, Kafka is designed to be able to work well at scale and to be scalable itself, and it does this in producing applications by using partitions. So in a particular topic, 1 or more partitions can be created. So in this case, you determine that. In this case, I've asked for 3 partitions. So I set that up when I set up my application. And what Kafka will do is Kafka will spread those partitions from a particular topic out across different brokers. And this allows us to really scale up producers really easily as we won't have to load one particular topic from one broker. We can add more brokers if we want to, and we can scale the load out more. So we're not placing all the load on one particular broker depending on the load coming into our application. So in Kafka, when it comes to consuming applications, we have this concept called consumer groups. So when you're thinking about consuming messages in Kafka, because of this stream history, we need to think carefully about how we're going to handle it if we have multiple consumers consuming from the same topics. So in other sort of messaging systems, you'd have sort of a queue-based system and you might have multiple copies of the queue for each subscription. And because messages are removed from the queue, consumers don't have this problem of potentially rereading the same messages as each other. But in Kafka, because of that stream history, which is a really great feature, we do need to be careful about making sure that our consumers aren't rereading the same messages or records. So to allow scalability of consumers are essentially grouped into consumer groups, and a consumer can declare what group they're in using some config called a group ID. So let's take a look at some examples of consumer groups. So here we've got 2 consumer groups. We've got consumer group A and consumer group B, and we have our topics and our partitions. So we have 1 topic and 3 partitions. So because in consumer group A we've got 3 consumers and 3 partitions, essentially it's just a case of matching them up, which Kafka does for you. So each consumer would read from 1 partition, and it's assigned 1 partition each. Now in consumer group B, there's only 2 consumers. So in this case, 1 consumer is going to be reading from 2 partitions. So that we can ensure that all the messages are being read. From an ordering standpoint, it's really important that each consumer, or that each partition is only being read by 1 consumer. because Kafka provides an ordering guarantee per partition. So the first consumer will get the messages from 0 in the correct order, but if we tried to make another consumer read from that partition 0 as well, we couldn't guarantee that ordering guarantee. So what about adding consumers? Because maybe we've got increased load, we need to add another consumer replica. Well, if we were to add a consumer to consumer group A, it actually wouldn't be any use. Because we've only got 3 partitions and we've already got 3 consumers in that consumer group, that last consumer wouldn't be assigned a partition, so it would literally just sit there being idle, not really doing anything. Now, it might be good if you perhaps wanted a spare in case one of the consumers in consumer group A went down, it could then take over, but right now it's not really doing anything, it's just sort of sitting there idle. So this is where it becomes important, because it's important when you set up your application to consider the potential load that your system might go through, and thus how many partitions you'll want depending on how many consumers you're going to have in each consumer group, because they can only be matched on a one-to-one basis. So you can add new partitions once your system's up and running, but you need to be aware that the more partitions you have, the more load you're putting on a system when a leader election happens, for example. And the important thing to know is that ordering is only guaranteed while the number of partitions remains the same. So as soon as you start adding in partitions, you lose that ordering guarantee once again, which is why it's important to consider this, how many partitions you're going to have based on how many consumers you think you might need at some point when you're setting up your system. So that's something to consider in order to make your consumers and your consumering applications really elastic and scalable. So how do we actually go about writing Kafka Java applications that are reactive? So here is the standard Java Kafka producer and the standard Java Kafka consumer. Now, these they haven't been designed to be used in reactive applications. So although they have methods like pause and resume, which can help, they're not really designed to be used to be reactive and asynchronous and responsive like that. In fact, if we take a look at back pressure in sort of the standard Kafka consumer, the standard Java Kafka consumer client, it can be used to handle sort of short, unexpected fluctuations in load without becoming overwhelmed, because Kafka provides this sort of buffer in between your applications. It can be used for a little bit of sort of buffering. So Kafka consumers are pull-based, so they request new messages using this poll method. So this pull-based mechanism of consuming allows the consumer to stop requesting new records when the application or downstream components are overwhelmed with load. So in a really simple use case, back pressure in this case is enabled by only polling for new records when all previous records have been processed. So you can see here in step 1, we've got that synchronous call to poll in that while loop. This blocks until records are received. Then in step 2, this is where we're processing our records, so we can't poll any more records until that processing is complete. Then in step 3, once all of the records have been processed, the code can restart the loop and can call the poll once again. So this mechanism of consuming can work really well for simple use cases that can be modeled in this sort of single loop in a single thread, and where processing is fairly quick. But it doesn't allow for processing to be distributed, for example, like parallelized across multiple threads to better use resources within the consumer application. So actually, this is where it can be really useful to start looking at some of the reactive frameworks and toolkits available that provide a separation between things like the polling and the processing to enable better resource utilization and enable a more asynchronous style of consuming from Kafka, for example. So let's take a look at some of the frameworks and toolkits available. So this is not an exhaustive list, this is just some of the examples that you could utilize, and they are all open source, which is fantastic. So we've got here, the ones we're going to be taking a look at are the Alpaca library, which is a Kafka connector to other libraries like Akka. We're going to be taking a look at the MicroProfile specification, and then lastly taking a look at Vertex. And actually back pressure works differently in each of these, so it's quite interesting because depending on sort of the style of application you're writing and your requirements, different frameworks and toolkits might be more applicable and more appropriate for your application than others. So let's take a look at Alpaca. So Alpaca is actually a library within the Akka framework, and Alpaca Kafka connector is essentially what allows it to connect into Kafka. So it allows sort of consuming and producing from Kafka with something called Akka streams, which actually leverages the reactive interface of the streaming library, and this is where the back pressure comes in. It actually helps to hide a lot of the sort of complexity, especially when your streaming logic is non-trivial. So like substreaming per partition and handling commits in custom ways, for example. The interesting thing about this framework, before we get onto the back pressure in more detail, is that it's actually based on something called the actor model. The actor model is different to using something like microservices, for example. So in the actor model, the actors is essentially a conceptual model to deal with concurrent computation. So in this, it's the actor that's the primitive unit of computation. So it receives messages, does some sort of computation based on it, and these messages are sent asynchronously and received by actors in something called mailboxes where they're stored. So it's a different way of architecting your application. So if you're already using the actor model, or an actor-based application, then Akka and the Alpaca Kafka connector might be really useful for you to take a look at. But if you're based on, say, microservices, it can be a bit of a paradigmal shift to an actor-based model. So looking at back pressure in Alpaca, as I said, the Alpaca Kafka connector is actually a reactive Kafka client that is built on top of something called Akka streams. So it is able to handle all of the pull requests to Kafka, which really means that the application code to request new records utilizes this standard Akka streams back pressure mechanism. So this mechanism is implemented using the reactive stream specification that I mentioned earlier in the reactive programming part of this presentation. And it essentially works on the basis that imagine the application is split up into stages, where downstream stages advertise to the upstream stages when they are ready to receive more data or more records. So you can see here at the bottom, underneath each of those downstream components, there's almost like a mailbox, and you can see whether it's empty or full. And essentially it then creates this demand request upstream based on its availability in this sync mailbox. So this might be familiar to developers if you've used Akka streams before. But as I said, this does require a bit of learning, because you are having to sort of switch to the Akka framework. So let's take a look at another different framework. Let's take a look at MicroProfile. So MicroProfile is a community-driven specification for enterprise Java microservices. So it's really designed and created and built by a wide variety of individuals, organizations, and vendors within the community. So there are different APIs that come as standard as part of the MicroProfile specification, and there are many different implementations of this specification, including, say, OpenLiberty, for example, which is our open source application service. So in the standard MicroProfile 3.3 stack, you can see this bottom triangle are the APIs you get as standard with that. So you get things like CDI, config, health, metrics, open tracing, etc., etc. There are also, interestingly, standalone projects that the MicroProfile community also works on. And included in this is the reactive messaging specification that we're interested in. Now this specification actually makes use of and interoperates with two other specifications. The reactive stream specification, which is not a MicroProfile spec, but that's that community-driven specification that I mentioned earlier, which is the standard for handling asynchronous data streams. And it also utilizes the reactive streams operator, which essentially provides a basic set of operators to link different reactive components together. So how does reactive messaging actually work in MicroProfile? Well, it works by utilising annotations on an application's beans methods. So there are two types of annotations, and that's at incoming and at outgoing. So at incoming is when you're receiving records or data or messages, and at outgoing is when you're publishing them. And these two different annotations are connected together by something called channels. Now these channels can be internal or external to the application. So if they're an internal, they're just called channels. If they're external, so your application is trying to, say, connect to an external messaging broker, like Kafka, for example, then those channels are called connectors, because they are externally connecting. These channels are literally just opaque strings, so you can see here at the bottom we've just named one of them order, and that's how we're connecting method A to method B using that at outgoing order and at incoming order. So back pressure in MicroProfile Reactive Messaging works in a similar way to Akka, where essentially the flow to downstream components is controlled based on whether those components are making requests for data. So you can see sort of the basic flow of how this might work on the slides here, going through 1, 2, 3, 4. As I said, there are different implementations of MicroProfile, because MicroProfile is just a specification. You'll need to use one of the implementations. So that might be OpenLiberty, it might be Quarkus, it might be Smora Mutiny. There are lots of different implementations. These individual implementations of MicroProfile might interpret this back pressure request in different ways. So some might use the pause and resume functions, others might simply just stop the poll loop. So it's worth checking which implementation you're using to see what the back pressure might be like, or what back pressure method they're utilizing when it comes to utilizing MicroProfile Reactive Messaging. The last framework we're going to take a look at is Eclipse Vertex. So Vertex is a polyglot toolkit. So the others were sort of more Java focused. This toolkit can be used for Java, JavaScript, Scala, Kotlin, and many other languages. However, it does run on the JVM. It utilizes something called the Reactor Pattern, which is really focusing on this sort of event-driven architecture style. So it uses a single threaded event loop, which is sort of blocking on resource emitting events, and it dispatches them to corresponding handlers and callbacks. It's non-blocking, it's event-driven, like I just said, and it includes this distributed event bus, and it's single-threaded. So it's really important that we don't block the thread. So let's take a look at what back pressure is like in Vertex. So in Vertex, we're able to utilize this concept of sort of handlers. So this is, we found at least, this client gives some of the greatest flexibility in regards to its approach to back pressure. So it provides tools for sort of separating out the polling and the processing, which really gives developers the choice to either let Vertex handle the poll loop and use sort of pause and resume functions, or to handle the poll loop themselves. Now, there are different reactive libraries that sort of build on top of Vertex, so if these libraries don't fill your requirements, or you perhaps need some more control over your back pressure behavior, Vertex might be a great option because it is really flexible in that regard. We actually utilized Vertex in one of our demo applications when we were switching a Kafka-based Java application to be reactive. So our original application, essentially the purpose of this was just to allow people to test out whether the Kafka they designed and created and built was working correctly within their own applications. So all it does is produce events to a topic in Kafka and then kind of consume its own events, which isn't necessarily what you do in enterprise or want to do, but it is just for testing purposes. So we also have a front end in our application, and this is where we can input sort of the custom text for our records, and we can start and stop producing and consuming. So we actually used Vertex when we were recreating or adjusting this application to be reactive. And this is all open source. If you'd like to go check it out, feel free to go and take a look at our GitHub repository. So if we take a look at how this application works, essentially we were creating one where we could input custom data, then we could start producing, we could also start consuming, and we could see the records coming in from Kafka once they'd been created. And then we also wanted the ability to stop consuming and stop producing. And it was actually this stop-start coming from our sort of UI that was causing us some additional headaches, because in the original application, using the standard sort of producer client, the call to produce a record is a blocking call. So we had some headaches in terms of threading. But by switching over to Vertex, it meant that in our producer, we were able to now use a future to get back from the send function. So we were able to create a more asynchronous producer, which was great. And it was quite a small code change, so it was very easy to implement. And it's really important that we have this sort of more asynchronicity when it comes to reactive applications. But actually the biggest change we saw was in the consuming. So in the original version of the application, we were having to use this sort of for loop inside a while loop that resulted in this sort of flow that we see here that we went through before. But actually, when we were utilizing Vertex, we were able to utilize this handler function so that this handler could be called every time a new record came in. The problem before was that we were doing this polling where we had to poll records, grab a batch of records, wait for all those records to be processed before we could grab another batch. So it didn't feel very asynchronous. Whereas utilizing the Vertex Kafka client felt a lot more asynchronous because as every new record arrived, we were able to send it off to that handler function. So much more asynchronous consuming and producing of records, which fit much better with the reactive paradigm. And the changes made the flow a lot simpler too. So Vertex was now handling the step of polling for new records so that our application code could just focus on sort of the processing of it. So we were utilizing this pause and resume function from the front end so that we could do that stop and start from our front end WebSocket. And that meant that we didn't have to deal with this headache of writing logic to control the thread lifecycle and sort of synchronize data across threads just to get control over the flow of records. Vertex was able to sort of handle that for us in a much easier manner. If you want to check out sort of all of the different benefits we gained from switching from a non-reactive to a reactive Java Kafka application, we've actually written them all up for you to see in this blog here for you to take a look at. So hopefully in summary what I've shown you is that sort of just taking a non-reactive application, adding in Kafka does not make a reactive application end-to-end. You need to carefully consider the Kafka configuration that's best for your particular reactive system, and we would recommend utilizing some of the Reactive Kafka clients that are available through these open source projects, these open source toolkits and frameworks that can provide these additional benefits. But you're not alone. The open source community is on hand to help. Check out any of the open source Reactive projects we've mentioned. There are also others, like for example Project Reactor, that you might be interested in. So I'll quickly pause here and show you a brief demo of just how easy it is to get started utilizing one of the Reactive frameworks. So in this case, we're utilizing the MicroProfile Reactive Messaging specification for a Java Kafka-based application. So I'm just going to quickly demo how easy it is to get started utilizing one of these Reactive frameworks. So in this case, we're going to be taking a look at the MicroProfile Reactive Messaging specification and applying it to a Reactive Java-based application. So to do that, I've headed to our online environment. This is up all the time, so if you'd like to have a go with these interactive labs yourself, feel free. You can access them via the link I provided in the presentation. And you should see a page like this, which shows you some of the modules you can get going with around the Reactive space. So today, I'm just going to be taking a look at this first module. I've already got it open here. You'll need to log in using some social sort of logins. That might be GitHub, Twitter, Facebook, Google, or others. And once you've done that, it will take a little bit of a while to load. We're just setting up the environment in the background. Once it's loaded though, you should see instructions on the left-hand side here, your IDE on the right-hand side, and then if you go to Terminal, New Terminal, you should see a terminal appear in the bottom right-hand side. So this application, actually most of the labs that are in this environment utilize the same application. So it should be fairly easy to follow each lab because you don't need to get familiar with the application every time you start a new lab, which is really helpful. So this application, you can see a basic architectural diagram here just to sort of show you the different aspects of it. We've got a basic application utilizing, it's made up of two microservices. One of those microservices is the system microservice and the other one's the inventory microservice, and they're connecting via Kafka, you can see here in the middle. So the system microservice, essentially its job is to calculate and publish an event that contains its current average system load every 15 seconds, and it's publishing that event to Kafka. And then the inventory microservice subscribes to that information so that it can keep an updated list of all of the systems and their current system loads. We can access that information from the inventory microservice via this REST endpoint here. So you can see on the right hand side we're showing where we're utilizing MicroProfile Reactive Messaging and where we're utilizing a RESTful API. So without further ado, we'll get started and see how we can utilize this Reactive framework to really build a responsive reactive Java Kafka application. So let's just check I'm in the correct repository. Yeah, looking good. And I'm just going to git clone from this repository and then cd into the correct directory. Great. So this is actually all open source. So if you'd like to go and take a look at the code itself, you can head to GitHub and check out this code if you'd like to dig into it in more detail. So the first thing we're going to do is we're going to create this system service class. So this is for the system inventory. So this is the one that calculates the average system load and publishes that event to Kafka. So I've created it using a touch command in my terminal, and if I head to the Explorer, I should be able to follow these U signs to the file that I've just created. It makes it fairly easy to find in this IDE, which is really helpful. So you can see it here, system service class. So if we head to that, I'm just going to close the Explorer so it's easier to see the code, and then I can copy and paste in the code we provided here for you. So because this is the system microservice and it's publishing to Kafka, that means we're utilizing the outgoing annotation from the MicroProfile Reactive Messaging specification. And you can see we're importing it up here above. So we're utilizing this outgoing annotation and we are publishing to the Kafka topic system load, hence why that's there. As I mentioned in the presentation, there are things called reactive programming libraries, and many of the reactive frameworks utilize those libraries. One of them is RxJava, and we're actually utilizing that here in this application. So we're utilizing the flowable method it offers. Flowable was introduced in RxJava 2.0. In RxJava 1.0, it was only observable was available. Now, the sort of difficulty with observable is that it doesn't offer inbuilt back pressure, and that's where flowable was introduced in RxJava 2.0 as an alternative to observable that allowed you to enable inbuilt back pressure. So we're utilizing flowable.interval here to essentially use it to calculate and publish the message on the Kafka topic. And it essentially helps us set the frequency of how often we're going to be publishing that calculation. So in this case, every 15 seconds. So now that we've created it for the system microservice, and you can see a sort of a diagrammatic version of what we've just done, we're going to head over to the inventory microservice and set up a similar sort of class. So if we again do this touch command, and then if we head to the Explorer, this time instead of heading to system, we're going to head to inventory. So if we follow these U's down, and there's the class we need. So if we open that up and then close the Explorer and copy and paste this code in, and then we'll take a look at it. Remember to save, because essentially the builds won't be able to build if you haven't saved. It's not an automatic save on this IDE. So in this case, we're utilizing the @incoming annotation. Again, still looking at that same Kafka topic, so system load, and we're just consuming from Kafka this time. That's the main difference. So now we need to go ahead and create the MicroProfile config properties. So if we create it first for the system microservice, so again, we're going to head, instead of to inventory, we're heading to system. Wait for this to load. And instead of heading to Java, we want to head to resources, and then there's our MicroProfile config file. So if we open this up, oh, wrong one. There we go. And then we should be able to copy and paste in this code. So here you can see essentially the config that we need, and in this case, because it's the system microservice, we're utilizing that outgoing annotation, so hence the outgoing here. And as I mentioned in the presentation, we're utilizing a connector. So that's an external based channel. So it's a channel that connects our application to an external messaging broker. In this case, we're connecting to Kafka. Now each implementation of MicroProfile Reactive Messaging is different. So they all offer, or they may offer, different types of connectors. In this case, because we're utilizing the Open Liberty implementation, and we're trying to connect to Kafka, we're using the Liberty Kafka connector in our example here. You can see we've also got the topic name here for the topic we're trying to connect to in Kafka, and we've got a serializer so that we can essentially change our object into JSON for Kafka. So let's go ahead and create a similar file for our inventory microservice. So again, just creating that MicroProfile config properties file. We're utilizing MicroProfile config, which is another of the specifications in MicroProfile, and that really enables us to externalize the configuration from the main logic of our application, which is really helpful when we're creating sort of cloud native applications. So again, let's go and copy and paste this in. You'll notice it looks fairly similar, except this time we're utilizing the incoming annotation, hence incoming in this config properties file. Again, we're still utilizing the Liberty Kafka connector. We're still trying to connect to the same topics, in this case, system load. This time we've got a deserializer because we're transforming from JSON into an object. And this time we've got an extra configuration value. And that's because, as we talked about earlier in sort of the more Kafka-focused area of our presentation, Kafka has this fantastic ability to create consumer groups, which enables that order guarantee and make sure that you're not duplicating the processing of records within the same topic. So in this case, because this microservice, our inventory microservice, is a consumer from Kafka, we need to put in this group ID. So if we were to spin up any other additional inventory microservices, so replicas, for example, they would know to join the same group ID. We wouldn't have any duplicates, and we would have that ordering guarantee. So let's continue on. The next thing we need to create is a server.xml configuration file for each. Now we've already created the one for inventory because it's exactly the same as the system microservice one. So we're just going to show you how sort of the code within the system one so you get an idea of what's within it. So in this case, we want to go to Liberty, and then there's the server.xml that we need. So if we open that up and then copy and paste this code in and save, you can see some of the features that we're utilizing in our application here. So there's the reactive messaging feature that we're utilizing. And as I said, we're also utilizing several of the other sort of specifications or APIs that come as standard as part of that MicroProfile specification, like MicroProfile config, MicroProfile health, JSONB, and CDI. If you'd like to investigate more of those, we have some great guides on the Open Liberty website, which also utilize the same application that you can go and check out. If you head to openliberty.io and head to the guide section, we've got guides on each of these MicroProfile specifications if you'd like to check that out. So as I said, we've already done the one for inventory, it's exactly the same. So now we're going to move on to the Maven configuration file. So again, utilizing this touch command to build it just makes it a bit easier. So this time we're heading to system, but instead of Liberty, we're heading straight to system here. So I'll just close main so you can see it easier. So it's just under SRC. So if we open that up, so now we can copy and paste this code in. Scroll down to the bottom, this one's quite a large one. Copy and paste this in, and then save. So here you can see some of the dependencies that we're utilising in this application. I'll close my Explorer so you can see it better. So you can see here we are importing that RX Java dependency for the flowable that we're utilising. There's Apache Kafka. We're utilising the OpenLiberty guides like I mentioned. And here is the MicroProfile Reactive Messaging specification, which is separate from the Eclipse MicroProfile dependency because it's a standalone project and it's not part of that standard stack. So now that we've created our pom.xml, we can start to build the application. Now make sure that you are in the right directory. We need to be in start in order to get this going. So now that we've gone to start, we can paste those commands and it should start building or running the Maven install and package goals, and we can start to build our application. So we've done that one. Now we'll do a Maven package. Build success, fantastic. Shouldn't take too long. The next step is just to make sure that we've got the correct and the latest OpenLiberty Docker image inside our environment here. Because this is a shared environment, sometimes it can change. So we just want to run this just to make sure that our application is going to be okay and that we've got the right versions of everything. And once that's built, it will build quicker if you run another lab. Within this environment, the great thing about this environment is that it saves your progress. So that's why we have cleanup scripts at the end of every lab in case you do not want your progress saved and you want to go on to another lab. But essentially, if you do this Docker pull, it should mean that if you go on to another lab later and it asks you to do the same step, it should be much quicker because it should have already pulled for you. And as I said, this environment will be available afterwards. So if you'd like to have a go afterwards, absolutely fine. Feel free to try any of the labs on there. So now we're going to do a Docker build of firstly of our system microservice and then of our inventory microservice. And then we're going to run our script called start containers, which essentially starts up the containers that we need for things like Kafka, Zookeeper, and the microservices in the project. Because we're using Kafka, we need to use Zookeeper right now so that we can store the metadata that we need. There is plans for Kafka to release a version where they will be able to just store that metadata within a topic in Kafka and you won't need Zookeeper. But right now for this particular application, we do still need Zookeeper. And so that's why it's dependency within this application. So once we've got this application up and running, we're going to try and access the application by making a GET request to that REST endpoint I mentioned in the inventory microservice. So essentially what we're testing here is we're testing that our system microservice was successfully able to computate that average system load and send it successfully and publish it as an event to that Kafka topic, and that we're able to successfully consume from that Kafka topic via our inventory microservice, and then we were able to publish that to our sort of users via this REST endpoint. So it just took a little bit of time there just because we were downloading a newer version of Kafka from the looks of it, but it looks like we're all done now. So we need to cd back to this home directory. So let's go back there. So now that we've given it a bit of time just to get up and running, let's try this curl command just to check whether our endpoint is working. Great, so we've given it a bit of time and you can see here that we're now outputting what we should be seeing. We've got an example there on the left hand side in the instructions and we're seeing that system load, which means we have successfully connected our system microservice to Kafka and our inventory microservice to consume from Kafka, and we're able to access all of that information via that REST endpoint from the inventory microservice. If you run this curl command multiple times, you should see that that system load changes because this is live and it is being updated every 15 seconds. So hopefully that's shown you just how easy it is to get started utilising reactive frameworks and toolkits like MicroProfile Reactive Messaging in a Java Kafka-based application so that we can really make it as reactive and responsive as possible and enable our applications to give the best user experience possible. So if you'd like sort of a recap of what reactive systems are, when they're useful, how to go about building them, I've written this really short free ebook that you can access online via the link I've given here, which essentially gives you that recap. And if I haven't given you enough sort of resources to take a look at throughout this presentation, here are some additional resources you might want to take a look at. I really hope you've enjoyed today. I'll hopefully be taking questions after this, and if you have any additional questions, then please do reach out to me on Twitter. My Twitter handle is there. It's @GraceJansen27. Thanks so much for listening.
Мы заочно благодарим Грейс за такой классный, исчерпывающий доклад. Согласитесь, довольно динамично и интересно рассказывает. Жаль, что не удалось послушать ее прям так, вживую. Я напоминаю, что вопросы, которые могли у вас появиться по ходу доклада, можно и нужно писать в чат и засылать любыми другими каналами. Мы их соберем и передадим самой Грейс, для того, чтобы она могла ответить в то время, когда сможет. К слову, уже сейчас я запросил у нее те ссылки, которые упоминались в докладе, и надеюсь, что скоро мы сможем их расшарить либо списком самих ссылок, либо прям слайдами. А пока предлагаю сделать небольшой перерыв. Сейчас у нас в этом перерыве будет активность от нашего партнера Динс, будет довольно интересное интервью, судя по описанию, тоже с удовольствием его послушаю. Скоро увидимся.